Now, I would like to discuss about the energy principle for open channel flow. So, as we learn in Fluid Mechanics 1 and Fluid Mechanics 2, when one of equation that we use to solve Fluid Mechanics 1 and Fluid Mechanics 2 is Bernoulli equation. So, Bernoulli equation there is actually discussing about the energy of fluid. So, the Bernoulli equation, so we have energy here. So, and then it's equal to P over rho G plus V square over 2G and plus Z. So, means that the P here is the energy that being converted into pressure, and there is a kinetic energy, and also it has a potential energy. Okay, same goes to open channel flow. By right, it's still we still could apply Bernoulli equation. So however, because the pressure is always PATM, so means the Bernoulli equation that we need to apply in open channel just consists of kinetic and potential energy. So this is the first basic idea about the energy in open channel. Okay, so however, in open channel, we're not using terms of Bernoulli equation. So we are using a special terms called specific energy and total energy. So for specific energy, it can be written like this one. So we have E, which is the energy. So, and then it is equal to Y plus V square over 2G. So if you see the equation here, you could find that V square over 2G is similar with the Bernoulli equation. And Y here is the depth of flow. So the depth of flow means the 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 height of the water flow. So maybe it is equal to Z in Bernoulli equation, and then we don't have term of P over rho G because the pressure here is always PATM. So we assume that PATM is 0 because the calculation is based on gauge pressure. So the term of pressure here can be eliminated. So however, normally in open channel flow, we not remain the terms of V, velocity. We always change into flow rate. So we know that Q is equal to A times V. So and then we have V here is equal Q over A. And then because we have V square, so and then it will become Q square over A square. So now the equation of this one of specific energy is Y plus Q square over 2G A square. So and then the Y here is the depth of flow. So means that if you have a water channel here, this is the cross-sectional area, let's say. So and then the water level is here. So and then this is the value of Y. Okay, it is from the bottom of the channel until the free surface, mean until the surface of water which is contacted with atmospheric pressure. So this is the specific energy. Why we call it a specific energy? Because it only tells us the energy for this area only. It is very specific for energy inside that channel. So, and then we have another term called the total energy. So the total energy is actually, we calculate the energy to reflect the inlet and the outlet condition. So means that you need to take the whole height of the channel. So that's why the equation here will become the total energy, so it is equal to Y plus Z plus V square over 2G. So mean the Y here is the height, the depth of this open channel water. The V square over 2G is about the flow rate inside this, the kinetic energy inside that flowing water. And the Z here is the height of the channel bottom from the datum. So means that the total energy actually calculating energy for the total situation. So for example, we have a drainage here. So, and then this is the datum, means the level. So the total energy is the calculation of energy between this point and this point. So means that you cannot only calculate the height of this one, but you need to add with the height of this one, because this height is actually will reflect the total potential energy that exists in the flow. That's why we call that as a total energy. Okay, this is a simple example. So let's say we have a rectangular channel. The width is 2 meter, the depth is 1 meter, the flow rate is 4 meter cube per second, and the height above that term is 2 meter. So if we want to calculate the specific energy, so this is the calculation. So y plus v squared over 2g. So we could calculate the v here by having q divided by a. So from the diagram here, we could know that the A is 2 meter times 1 meter. So, and then we could calculate, we could get the specific energy is 1.2 meter. So, and then to calculate the energy, to calculate the total energy, we need to calculate from the bottom datum here. So means that the specific energy is 1.2, and then we add an extra of 2 meters, so it will become, the total energy is 3.2 meters. So and then we need to calculate the specific energy diagram. So in fluid mechanics 1, I think we already learned to calculate or to draw the energy grade line. Energy grade line. Okay. So it's telling about the increment of potential energy, the decrement of kinetic energy, and so on and so forth. So the same thing goes in this chapter. So we need to draw the specific energy diagram for the open channel. So we start from the specific energy. Okay, so we know that specific energy is equal to y plus v squared over 2g, or we could write as y plus q squared over 2g and a squared. Okay, so from this term, we could say that, okay, because we have a velocity here, so we call this one as the kinetic energy. So, and then the y here is showing the height of water level. So we could say that the y here is actually the static energy. Okay. Because in the fluid mechanics 1, in flow in pipe, maybe we could say that the y is the potential energy. So, but in open channel, we say that it is the static energy. So then, we need to draw the diagram here, okay, for both, for static energy and also for kinetic energy. So means now we separate the equation. We could say that this is the static energy is equal to y. So and then if we draw a diagram, a graph, so let's say we have E and E here for the x-axis, and Y here is the y-axis. Okay, so and then we could say that E static energy will always equal to the height of y. So means that we could draw a straight line graph like this. So means at any point, the value of E must be same with the value of y. So means that if E is equal to 10 meter, so means the y here is equal to 10 meter. Okay, I hope you could simply understand about how to draw a diagram for static energy. So, and then we draw the diagram for kinetic energy. So here the equation for kinetic energy is Q square over 2GA square. So here we have a little bit problem because we have actually two or three-dimensional equation. What we mean by three-dimensional equation, so here we have an area and also the meter cube. So the Q. So the unit for meter cube, the unit for Q is meter cube per second. So means that you need to know, let's say we have a channel here. So we need to know the width of the channel. We need to know the height of the channel. At the same time, we need to know the length of the channel. If not, we cannot get meter cube. We cannot have three type of meter. Okay. Okay, so because we want to reduce the calculation here, so what we could do is we substitute the value of Q with the specific discharge. So what is specific discharge? It can be termed as, it can be shown as Q is equal to capital Q divided by B. So means that we try to simplify the equation. So means that if we substitute the value of Q square over 2G and A square with the Q is equal to, so means it is equal to Q square B square times okay, Q square is Q square of times B square. So and then we have a 2G here and then the area here. So area means the width times the height. So the width is actually the B and the height is equal to B square over Y square because BY square. So and then from this equation we could neglect the value of B actually. So B means the width of the area. So and then if we neglect the value of B, so we could write the kinetic energy now can be calculated by using the idea of Q square over 2GY square. So this is the idea of this one. So the basic idea is actually to reduce the term in our equation. So please remember this, and then please remember the kinetic energy is equal of Q square over 2GY square, which is the Q here is actually the actual flow rate divided by B, divide by the width of the channel. Okay, let's say we have an example for this one. A rectangular channel, width is 4 meter, flow rate is 12 meter cube per second, and the depth of flow is 2.5 meter. Draw specific energy diagram and find critical and alternate depth. Okay, so maybe we just answer the specific energy diagram first. Okay, we know that the equation for energy is shown like this. So we have energy is equal to Y plus Q square over 2GA square. And then we simplify with using the idea of specific discharge. So and then it will become E is equal Y plus Q square over 2G and Y square. And so and then the Q here, okay, it is equal of Q over B. So and then if you calculate the value of Q over B, we could get it is around 3 meter cube per second. Okay, so what we could do? Okay, so the first one, for static energy is quite simple because the equation is very simple. E static is equal to Y, so means that for sure we could get a straight line like this one. Okay. So and then in Excel, if you plot this energy, you will say that if y is equal to 2, so for sure the static energy is equal to 0.2. So if you plot this in Excel, you will get the line shown as this one. So this is the line of static energy. Okay, so that is for static energy, and then we go for the kinetic energy. So we know that kinetic energy, so the equation is q square over 2a and y square. So, I'm sorry, 2g y square. So what we do is we try to plot this graph. So let's say if the y is equal to 0.2, so we could substitute the value of y 0.2 in y, and the value is q is actually calculated here. So we substitute the value and then we could get the idea of kinetic E. So it is equal to 11.4679. So and then if we do this in Excel, so we could plot the graph as this one. So the graph will become like this. Okay, so means that the straight line here is static, so, and then the curved line here is kinetic. Okay, so we have two lines. Okay, so then finally we need to draw the total energy line. So how to calculate the total energy line here? It's very simple. We just add the value of static energy here with the value of kinetic energy. So if you could see here, the amount of static energy will become higher and higher because the value of y is become bigger and bigger. But the kinetic energy, it will become slower and slower. So what is the rationale of this one? Because you know the flow rate is the flow rate is always constant. So if your y is increased, so mean the cross-sectional area is increased. So means that to balance the continuity equation, so means the velocity or the kinetic energy must be reduced naturally. So that is the idea. So means that if we plot the total energy here, so if we plot the total energy here as x-axis and the y here as y-axis, so we could found that the curve is showing like this. Okay, so the rule of thumb is, if you write this one, please make sure the static energy you drawn like this, a straight line from the origin. So and then the kinetic energy you may draw like this one, a curve from x axis to the right side. So and then if you asked to draw the total energy line, please draw like this one. So it must be lay between these two lines. So we have the static energy here and we have the kinetic energy there. So the total energy must stay at this region. So you must draw like this one to get the full mark. Okay, so this is the idea how to draw the total energy diagram. Okay, so what we could get from the graph, so we focus on the total energy line here. So in total energy line here, you will find that the curve is actually the quadratic curve. So and then it will have one maximum point here. Okay, so at this point, the maximum point here, so we call it as a critical depth. So mean the height of this one we call as the critical depth. So and then the energy at this point okay, we call it as minimum energy, because at this point the energy will become very minimum. So and then for another point, for example, we have at location here, okay, and then we have one point here and one point here. So at this point we found that the energy, okay, here is equal to E1, for example. So and then we write as E1 is equal to E2. Why we write E1 equal to E2? Because this point, the energy occur when the Y is equal to Y1. But okay, same energy can be get if the Y amount is equal to Y2. So mean that because we have 2 points of energy sharing, means two different height will give you same amount of energy. So we'll call these 2 points as the alternate depth. Okay. So what is the difference between the lower point and the upper point? So what is the difference of this one and this one? Okay. So the difference is at this moment, okay, at this moment we found that the Y is smaller. Okay, the Y is smaller, but it will give you certain amount of energy. So and then at this point, so the to reach this point, the amount of Y2 is bigger compared to Y1, and then it could create a same energy. Okay, so and then we could say that from this point, we found that the increment of energy is rapid. It is the increment of energy is rapid, is very high. It is rapidly increased. However, from this point, the energy is slowly increased. So here, because the energy is increased rapidly, so there are one phenomenon called the hydraulic jump will occur. Okay, so means the hydraulic jump means the energy is higher here, but the value of Y is actually lower and lower. So mean it is not fulfill the idea of continuity equation. So normal, so means the increment of energy, okay, will become so rapidly. So and then it will suddenly increase the value of Y. Okay, so at this stage, at least you could know that you could know how to draw the total energy diagram, and then you could label the maximum, the critical depth here, and also you could know how to determine the alternate depth.